Hello again, and welcome to video 3 of 4. So we're getting there with this project. So where we last left off, we were looking at this generalized linear regression. Um, you can see that these residuals are very clustered, which the spatial autocorrelation confirmed. And I told you at the end of the last video we were going to have to run a geographically weighted regression. So I'm going to go ahead and run that, and then I'll explain to you why we're doing what we're doing. So for this time, you can just type in GWR because it actually says GWR in it, which is why it works for searching. Make sure you're, again, in Spatial Statistics tools. Um, we are back to our input feature being the stats variable 20, the dependent variable again, poor mental health days. I can click select all and then just make sure I uncheck my dependent variable and any variables that failed the generalized linear regression. I believe that is it. When we name it, again, I just called it stats variable 20 GWR1. The things that you have to change here, first you have to change the neighborhood type. So we're going to do number of neighbors like we did in spatial autocorrelation. And then this is essentially just kind of running a test. So we're going to do what's called a golden search. It's looking for the maximum number of neighbors needed to get regionality in the data. We're going to do 100 to 200. So remember, 100 counties is about 4% of our data. I'm choosing 100 and 200 because I've done this a lot, and I know that for the United States, that's a good amount. If you were doing this for the first time, you could always do manual intervals and you could set minimum at 100 and increments however you want. One thing about this is if your number of neighbors is not high enough, the tool will fail. It'll fail for other reasons too, but that's one of the reasons it'll fail. We don't have to do anything with prediction or additional options. So go ahead and run this. And then here is the results. So look at the difference between weighted regression and linear regression. Remember, linear does not take into account space, weighted does. So big difference, much less clustering. And then let me pull up the reports. Okay. So this is the message you get for geographically weighted regression. First of all, we're doing a golden search, so it gives us that. We'll come back to this. It just lists the variables and it gives you an R-squared value, which we'll notice is higher than the linear regression. But here's the problem with going straight to weighted regression without weeding out variables using linear, is it'll just fail. It'll just fail and it won't tell you why. It'll just say failed due to multicollinearity, and it won't give you a reason. So if your model is failing, and it doesn't have to do with the fact that you didn't choose enough neighbors, because I did specifically mention this, you have to go back to generalized linear regression and see if you missed something in the reports. So that's why we bother doing it. Really, at this point, we're just kind of fine tuning the model. We're making sure that we can get a random distribution. All right. So why do we do golden search? Well, we're looking for this AII or AICC value, and that, yeah, I did. The other report tells you what that stands for. So what you're looking for with this AICC is the lowest number possible. Now, keep in mind, these are negative, so the lowest number would be closest to 0. So in looking at these, lowest number would be, I think 153. 35, nope, 100, 3, 4, 5, 6. Let's see if we can find anything lower than 3, 4, 5, 6. We can't. Okay, so 100 neighbors gives us the lowest value possible, 3, 4, 5, 6. So that is going to be the number of neighbors that we run. Um, so the next step then is to run the geographically weighted regression again. We're going to call it 2. And this time, instead of doing a golden search, we're going to do a user-defined search where we type in a number that had the lowest value of 100 and we run it. This time here is my output. It is not super different than the first one. Little bit of an improvement. If we look at the report, this one. Yeah, so we're up to 0.95, which is a little bit higher than it was the first time we ran it. The number of neighbors was close. It picks a random value. But here, 0.95, that's saying it fits the model about 95% of the time. Okay, so finally, we don't think this is clustered, but we need to prove it's not clustered. So that is that spatial autocorrelation again. So we're going to go back to spatial autocorrelation. Remember, the input feature is the geographically weighted regression, number 2 this time. The input field is a lot further down. We have to do all the way down to the bottom standard residual. Don't forget to generate report. We're going to do the k nearest neighbors. And this time we're going to run 100 neighbors. That's what the golden search tells us. So go ahead and run that. Remember, you just get a report. You don't get a map. That should be this one. Let me move that up. And there it is. So right now I have a z-score of 0.8, which falls within the random category, and a p-score of 0.3, which is a little high. What that tells you is that this pattern does not appear to be significantly different than random. That is what you're looking for. Random distribution of residuals tells you that you modeled the behavior as accurately as you could, given the variables you have. All right. So the final thing we're going to look at in this video are the 7 regression tests. So we're going to pull this over. This is linked in the doc. And I'm going to try to split my screen here. We'll see how much of a disaster that is. Doc my contents for a minute, and we'll come back to it. Okay, so we are in this part of the document, 7 regression tests plus misspecification. Misspecification you can't really test for. If your model fails, it just means you're missing some variables. That's why it's not in the 7 tests, it's just extra. So first of all, nonlinear relationships, curve linearity. The way you test for that is you go to your latest weighted regression, so number 2, and you open up the scatter plot matrix for that. So we're just going to pull that here so you can see it. And looking at all of these data sets, none of them are curved. They all have some degree of linearity to them. Next test, data outliers. That one you have to look at the standardized residual versus predicted plot. We have a couple of outliers. I could probably take those two out, and maybe a couple down here and run it again and get a more accurate model. But they're pretty close. For non-stationarity, you look at your map. There really aren't any groupings that are the same color. I mean, a couple, maybe. Like, here's a little bit of one. Here's a little bit of one. But for the most part, it's pretty random throughout. And especially if I turn off states and it loads all of the things, there isn't a lot of regional grouping. Multicollinearity. You have to go back to your scatter plot. Probably shouldn't have closed it. That's on me. And what you're looking for are straight lines that match up. And I don't even think I have a single straight line on, except for this one, poor physical and poor mental. They go hand in hand. But what it's looking for here are ones that are not in your main column that are identical, like those two. So passes that. My favorite word, heteroskedasticity, I think. That one, we're going to go back to the standardized residual again. This time I didn't close it. And what you're looking for is an even distribution throughout. You don't want it grouped at one end and spreading out toward the edges. What this tells you is that there's more of a relationship at low values than there are at high values. And here, really, it's pretty spread evenly. You could say maybe there's a relationship at middle values, but again, you also have kind of these corners, so it's pretty well spread. Spatially autocorrelated residuals also goes with non-stationarity. So again, you're looking for, wrong map. You're looking for areas that aren't grouped. So right here, you're seeing that it's not grouped, and we know that because we ran the spatial autocorrelation tool. And the final one is the non-normal distribution bias. Now, this is specifically for the map, not the individual variables. So what it's looking for is this distribution of standard residuals right here. And it's not very skewed. Our mean is a little bit off of 0. So it is slightly skewed to the left, but not significantly. And all of these little things kind of added up, like slightly skewed, slight clustering, some outliers. That is because it's not a perfect fit for your model. The thing that I could probably fix the easiest is to take out some of those outliers, but nothing is really, really standing out. And the model passed with a random distribution, so it's pretty good. All right, we are almost done. You have, at this point, generated your model. So if you think back to what we're doing, I am trying to model how many mental health days, not mental health days, how many poor mental health days people are reporting in a county. And I'm measuring that with about 95% accuracy with less than 1% random or less than 1% chance that this pattern is not random. So pretty good. What we're going to do for the last part is actually try to predict future data. So I ran this for 2020. I actually have the data for 2024, so I can run it. You don't have the election data for 2024 yet, but you will by the end of this year. So we're going to do part of video 4 now, and then we'll do the other part later. All right, video 3 done.